Hi folks, we're going to take a look at the solution to number 7 from page 145. So they give us this enclosed region that's split into two equal parts, and they tell us that we have 1,000 meters of fencing, and we want to find the dimensions that will maximize area. Okay, now you got to be careful here, because even though we're working with a rectangle, because of this extra side that we're including, we can't assume that the answer is going to be a square. Okay, so we'll see. It could be, but we shouldn't assume since we've got some extra constraints here. So first thing we want to do, if we follow our optimization algorithm, the first thing we want to do is find what it is we have to optimize. Okay, and in this case here, it's the area, the total area that's enclosed. So that's given by, well, the length of this field is 2x, and the width is y. Okay, so this is what I have to optimize, but as we've seen many times, there's two variables here. So this is where we're going to use the constraint. In this case here, the sort of the perimeter, including that middle fence, to help us hopefully write one variable in terms of the other. Okay, so if we take this 1,000 meters, what does it encompass? Okay, well, it encompasses these three sides here, which are all y, so 3y. Okay, and we've got these two sides there, so each is 2x, so 2x plus 2x, so 4x. Okay, so here now we have an equation that relates x and y. So we just have to decide which one we're going to isolate. Now I think I'm going to isolate x, because at least when I divide out the 4, it'll divide out nicely into the 1,000, where the 3 won't. Okay, so we'll have 4x equals 1,000 minus 3y, and x is going to be equal to 250 minus 3 over 4y. Okay, so now that we have this, we can input it into our area equation. So we have 2 times 250 minus 3/4 y times y. Okay, and I'll distribute that out to get something easier to differentiate, because there's really no need to use the product rule here. So we've got 2 times 250 is 500 times y, so we have 500y. And then here we have 2 times 3.4, so that'll reduce to minus 3 over 2 times y squared. Okay, and we realize here that we have just a quadratic. Okay, so nice and easy. We also see that it's a quadratic that's opening downward. So right off the bat, we can, this is sort of a known fact now that quadratics opening downwards will have absolute maximum. Okay, so here my derivative is just going to be 500 minus, so bring this down, so 3 over 2 times 2 is just going to be 3y. Make this equal to 0, and so y is just going to be equal to 500 over 3. Okay, now here this is an absolute max. Okay, I don't even really have to test anything, since it's a parabola opening downward. Okay, that's, like I said, that's we'll take this as an established fact because of the negative leading coefficient. Okay, so here we have our I guess our width here. So now let's find the other dimension. So x is just going to be equal to 250 minus 3 over 4 times 500 over 3, which of course I'm just getting from this relationship here. And so 3's cancel out. So here we have 250 minus 500 over 4 is 125. So here we got 125. Okay, so our final answer is going to be x is going to be 125 meters, and y is going to be equal to, and since this is an application question, we should be getting an approximation. So here we've got, what is it, 500 divided by 3, and that's 166.7. Okay, so there we have it. So again, here they gave us the diagram, so that was a big help. What was important to realize was that this 1,000 meters also included that middle portion when we were finding our perimeter relationship. And of course, when we found our area, to remember that we needed to take 2x. Okay, that's it for this one.